Good afternoon, everyone, and welcome to a live energy analysis aligning budget and energy conservation goals. I'd like to take a moment to introduce your speakers today. My name is Tina Hendricks, and I'm part of the Wildan Outreach team. And today I'm also joined by Ton Dip, who is part of the Wildan Project Management team. Wildan is a nationally recognized energy efficiency consultant, and we work with the 4 investor-owned utilities in California, which are PG&E, Southern California Edison, San Diego Gas and Electric, and SoCal Gas. PG&E does offer several energy incentive programs, including the California Energy Design Assistance Program, also known as CEDA, which focuses on new construction as well as major renovation projects. This program provides energy modeling services and savings calculations so that customers can get incentives when implementing strategies above and beyond the energy code. And we also handle all the paperwork for our customers. With CEDA, we really strive to make the process as streamlined as possible. We collaborate with the project team fairly early in design. And we hold 2 virtual meetings in order to evaluate the project scope and energy efficiency goals. That way we can run a whole building energy analysis, which will help the team determine the best strategies for their project, budget, and goals. Then once the project is built, the utility provides incentives based on the strategies that were actually implemented. As I mentioned before, today we're presenting a live energy analysis charrette on how to align budget and energy conservation goals. The course is available for credit for AIA members, and certificates of completion are available upon request for both AIA members and non-AIA members. Shown here is the AIA course description, which has been listed in the promotional material. And here are the learning objectives for this course. I won't go down the list. Essentially, at the end of this course, participants will be able to recognize the value of early energy analysis in the design process and how that can increase energy savings opportunities. All right, so here's the agenda that we have set out for you today. First, we'll set the stage with some key terms and concepts. Then we'll dive into the energy analysis exercise, in which we'll take a real case study and run a few what-if scenarios to evaluate different conservation strategies. After that, we'll reveal the built project results and review some key takeaway concepts. All right, we're also going to do some polling throughout the webinar. So if you have access to your smartphone, if I could ask you to go ahead and text number 22333 to J Huntsman 632, just like it shows on the screen, JHUNTSMAN 632, and that will get you logged in to the Poll Everywhere app. They do not ask for any personal information. It's just simply for us to do some polling during the charrette. So we'll go ahead and give you a second to go ahead and again text to 22333 J Huntsman 632, and then we'll go ahead and do a sample question, a test question, just to make sure that we're up and running. And the first question is, what superpower would you rather have? A, flight, B, invisibility, C, time travel, or D, crushing deadlines with your fist. So if you'll go ahead and text A, B, or C, we can make sure that our poll is up and running. And let's see if we've got any real-time results coming in. All right, it looks like we do. Give everybody just a minute to get their poll up and running. And if you make a mistake and you want to put another answer in, you just type in the word clear. All right. Looks like we might be up and running, Tom. So why is energy efficiency important? Let me begin by asking, how do we get to a clean and cost-effective energy future? We know that reducing the energy consumption of the built environment is vital to success. And as design professionals, we have an important role to play in cutting consumption. Could it be as easy as adding solar to every rooftop? Unfortunately, adding renewable energy generation without first implementing energy conservation measures can have detrimental effects to the grid, which is why we need to exercise our creative problem-solving skills in order to reduce the load of the building as much as possible. All right, we're going to do another poll here. Time for another poll. The question this go around is, what types of projects tend to implement more energy efficiency measures? So residential A, commercial B, retail C, civic D, institutional E, or industrial F. So if you have the app still up on your phone, go ahead and enter your response now, and we'll see if our poll will give us some data. Looks like we've got one response coming in, or 100% so far for commercial. We'll give everyone just another minute. It is kind of a tricky question. All right. So energy use intensity, moving right along. In our discussion today, we'll be talking a lot about EUI, or energy use intensity. For those of you that aren't familiar with it, energy use intensity is a key performance metric to understand how buildings use energy. It's measured in kBTUs per square foot per year. You can consider it similar to MPG, or miles per gallon in a car, but in this case, you want the lowest number possible. So how does that work? We take all the energy needs in a project, heating, cooling, lighting, anything that makes your meter spin, and divide that energy consumption by the square footage of the building. By doing so, this normalizes the value independent of the size of the project. So we can compare the efficiency of a smaller building to that of a larger building on a per square foot basis. And the resulting number is the EUI. You might be familiar with the difference between site EUI, which looks specifically at on-site energy consumption, and source EUI, which also takes into account efficiencies in generation and transmission. But for today, we're keeping it simple and we're just looking at on-site EUI. So where do we start? Okay, I'm going to hand it over to Tan. So he's going to walk us through even further and define other parameters for us. So Tan, where do we start?
So far we kind of talked about the big picture of energy efficiency, basically the impact on the grid, and more importantly on the site. So right now we're going to dive in a little bit further on the energy efficiency of the building itself. So here we have an example of some efficiency strategies that you might want to consider. We have some additional and some more. And next thing you know, you become overwhelmed and you're unsure of where to start. So how do we cut through all this and make sense of what's going to be best for the project itself? So let's clear the slate and let's start with knowing what the goals should be, or what would be normally for most owners goals would be. Obviously, each one of these goals are a little bit different and they will lead you down a different path within your design. So it's important to understand which one of those goals are going to be. Obviously, if you look at EUI, you might have a different path to go compared to what the payback would be. So understanding those goals is always the first step in deciding where to begin. Once when you have your goals, it's a good time now to strategize. Well, what strategies do you usually use? Rules of thumb, maybe looking at manufacturer's literature and deciding upon particular equipments that way, or maybe looking at EUIs, comparing one building to another as a result, but also more importantly, looking at energy models and comparing what those efficiencies would be in the building strategies that you would normally choose. So here's a quick poll. What's your current method that you would go with? A, rules of thumb, B, product literature, C, comparison of one project to another, or D, energy modeling. So it looks like comparison of other previous projects, probably a common one that most folks right now on this presentation would normally do. Now, what's important is also when we're comparing things, we're comparing two identical things together. You know, it's the old adage, are you comparing apples to apples, right? So when we're comparing buildings, take for example, we can easily take an example of a retail building in the same location, so identical climates, same function types, same square footage, window to wall ratio, and then hours of operations are identical. But let's say we reorient one of the buildings by 45 degrees. You'll be surprised that the energy efficiency or usage is going to be slightly different compared to the two, even though everything else, all the variables are almost identical. But because we reoriented the building by 45 degrees, because it's been reoriented by a different way, the sun may be impacting into the building a little bit differently. So that would essentially affect what maybe your cooling loads would be. Maybe your lighting loads would be a little bit different as well. So those are going to be key factors in deciding and comparing everything. So when we look at these energy conservation strategies, we want to look at three scenarios, right? So we look at usually, you have code, and then we have something like a good, better, and best. Good typically being your current design, where it currently sits. Better, improved strategies above what the baseline threshold would normally be. And then best, basically, if cost wasn't a factor and if everything was available on the table, what would be the best solutions for you? But obviously, we're trying to have that good balance between initial costs and energy savings of the building itself. And the best time to start energy savings is as early as possible. So usually if you're in schematics or design development, it's a good time to start considering an energy model for this. Because the earlier you have, the better impact you can have within the design scope with minimal impact to what cost would associated be. More importantly, you always also want to prioritize minimizing the load first prior to implementing any effective energy efficiency measures. And then you can look at renewables or alternate energy sources, and then you could consider the operations and building usage as well. But usually it's best to reduce your load first. We talk about reducing load first mainly because if you hear about the duck curve within California, or it's actually not even just in California, but also nationwide, there's a huge ramp up to when we could install a lot of photovoltaics and renewable energy, but the problem is it's generating usage at the wrong time. And so there's a ramp up to when the sun starts to go down to when we need that energy to go up. And that usage starts to increase now that photovoltaics are not generating energy when we need it. So that's what causes the duck curve. Reducing the load first helps flatten that curve a little bit. So then this way, we don't need that high demand immediately or so quickly. I would like to just pause to see if there's any questions. Okay. So moving along here, when we're doing a comparative analysis, we always take into account of what the building geometry would be, hours of operations along with the weather, and we're looking at the minimum requirements. When we're talking about minimum requirements, we're talking about the type of equipment, like your HVAC, your service water heaters, the plug loads, or any type of heavy equipment that may draw higher loads within the building. And when you're doing a comparative analysis of these model results, essentially what you're doing is you're keeping your geometry and your operations exactly the same, and then swapping out some of those equipments of your HVACs or additional loads and efficiencies to see what that comparative analysis is, or those results would be from each other. Because at the end of the day, when you look at these efficiency measures, it's not a straight addition of what those energy savings would be. So that's why we have this math problem of 2 + 2 does not always equal 4. It's 3.25. So a great example of this is maybe LED lighting. Fairly easy, achievable item for a lot of people to do. But the problem is with most LED lightings, it helps reduce the energy load. So in return, it helps with cooling loads during the summer. But it doesn't help with heating loads in the winter, because if, let's say, you had a different type of lighting compared to LEDs, those lighting systems will emit some heat. So that kind of adds to some of the heat that would be passively generated within the building itself. So then you may not necessarily need to heat up the building as much during the winter. So it's kind of a give and take, and you're trying to find that balance. And we said before, it's not a straight addition of energy savings. It's how everything interacts with each other at the end of the day. So going back to that long list of energy efficiency measures, let's wipe the slate clean here. And let's just focus in on these 6 measures instead, or categories. We'll concentrate on the building massing, the envelope, lighting controls, HVAC, and demand control, along with energy recovery. Here. And here for this live exercise, we're going to use a school project as an example. I understand that this project is going to be in the Midwest, and it's going to be in a different climate zone than what we're used to here. So obviously, for us, in our climate zone, we're more in climate zone 3, under what IECC would refer to. But in this particular case, this project is in a climate zone 5. So I'll point out the different strategies that we might consider for California instead. But for this exercise, we're going to have a project based in the Midwest here. So, quick pop quiz. These are going to be 4 different combos of strategies here. Now, I'm not providing a lot of information here, so this is going to be your best guess, or what your first blush would be of what would be the best combination of strategies that would provide the most impact to energy efficiency. So if it's A, it would be essentially upgrading the envelope, where you would have higher R values for the exterior walls and roofs in combinations with daylighting controls. Or is it B, combinations of compact massing along with the improved envelope and maybe energy recovery? Or C, compact massing and geothermal HVAC system with an energy recovery system? Or D, daylighting controls and HVAC demand controls? So with that, which combination?
Real quickly, we have a question in the chat if it's an existing school upgrade or a new ground up construction.
It is a new ground construction.
Thank you.
So with that, what is the best combo of strategies that you have in mind here?
Yep, you can go ahead and enter that into the, by texting 22333 and entering J Huntsman 632. That would allow you to participate in the question.
Looks right now, everyone feels the daylighting controls and HVAC controls would be the best combo of strategies.
Correct.
So with those 6 energy conservation measures we talked about a few minutes ago, right now we're going to go into the details of each one of those strategies for you. We are going to have some costs behind this, but usually some folks, for the sake of cost, because cost does vary, we're going to use dollar symbols as a way to show costs. So we're going to have maybe a budget of $12 symbols to spend on this particular project. So think of it like coins. And we're going to max out at $12 symbols. And as we go through this, think about how each one of these measures or efficiency strategies would play and what the combinations would be. Everyone kind of already selected D, the combination of the HVAC, lighting, and controls. So we have that in mind. Let's see if as we go through some of these additional information, if it changes everyone's mind. Okay, so let's start with the building massing. So here on the left, we have a dispersed form. Obviously, the square footage are exactly the same for both. You could see here on the dispersed form, glazing is a little bit higher. It's about double compared to what that window wall ratio would be to the compact form. But you can see here the cost for the dispersed form is a little bit higher as well. Now, there's trade-offs with this, right? With the dispersed form and the higher glazing percentage, that means you have a little bit more daylighting coming in to a school project here. So that means you could possibly reduce your lighting power density within the school project. Now, the opposite would occur if you were to select the compact form, right? Where you might now have to increase your lighting density because now you don't have as much natural daylight coming into the building. So you may mention it's not, these energy saving strategies are not a straight addition. And so these factors play into each other, and energy modeling helps understand what these play are with each other in these strategies. Okay, so think about those. Let's move into the envelope upgrade. Now the base design option would be an R value of exterior wall of R16, your roof at R30, and then a common clear low E glazing, nothing too low as far as the solar heat gain will be, but also it would have a high visible light transmission, right? So now that means for the base option, you're going to have a lot of natural light coming into the building compared to an upgraded version of the envelope where you would have a higher R value for your exterior wall of an R24, your roof being R50, essentially looking at cutting down on thermal breaks. And obviously, when you're talking about thicker insulation, there's additional impacts worth considering too, because thicker insulation may also mean actual structural impact as well. So now your footing may end up increasing because that's additional load onto the exterior of the walls. So there's additional factors that would be behind the upgrade option in that decision. But also when you look at the reduced solar gain glazing, that would also mean your visible light transmission is also reduced. That means lighting power density might end up being increased. So there's additional factors needed to be considered, but you can see here the additional cost of an upgraded envelope is more than double the cost of what the base option would be. And then lighting controls, you can see here fairly insignificant as far as the cost goes. Basically, it's usually what we call the low-hanging fruit, not super expensive, easy to do. You could have standard occupancy and vacancy sensors, but having that additional added control that ties in with daylighting control. So then this way, the lighting power density basically changes to the current needs of where the current lighting is for the building. And with that balance of daylighting will help out in energy efficiency as well. And then your mechanical systems. Here we have an example of a base common system that a lot of folks end up using. It's a VAV system with an air-cooled chiller and a gas boiler, right? Or you can do a ground source heat pump, which is upgraded. For us in California, we would probably not lean towards a ground source heat pump. We might probably look at an air source heat pump instead because we're a little bit more milder, but seeing how this is in the Midwest, a ground source heat pump may be a little bit more efficient for them. So for us, we'll probably consider first a air source heat pump or maybe even a VRF heat recovery system over a ground source heat pump. But in this particular case, we have an example of a geothermal or a ground source heat pump instead. Obviously, the ground source is going to be more expensive. It's also going to be an additional impact because you will have to drill a number of wells in the ground in order to have the system operate properly. So it's going to have a higher base cost. And then your HVAC demand controls. Fairly simple. You can see you could go with your standard thermostat controls, which is no real additional incremental cost, but the incremental cost of the demand controls and having that tie in along with your daylighting, where it has a CO2 and occupancy sensors, may actually help out.
Tom, one more
Yes.
question. Excuse me. On the dollar comparison, is the only initial cost and not factoring in life cycle cost over a number of years?
Correct. We are looking at the initial cost more than anything else. So, when we're looking at the initial cost, because that's going to be what the incremental cost would be more than anything else, what that initial impact is. We're not factoring the life cycle cost. Obviously, if we were, you would have to start factoring what the annual energy savings would be, what that initial upfront cost would be, and then you can kind of figure out from there what that cumulative energy savings would be and how quickly that payback would be. But it's an individual basis for most components that a lot of folks end up looking. It's when you do an energy model, it's good to look at that cumulative for the whole building, right? Because usually if you actually just look at the individual cost payback for a lot of these items, and I'll go back here. The paybacks, the long paybacks are going to be in your envelope upgrades. You're going to see a lot of times if you just look at the individual aspects of those, your envelopes are going to have like 60, 100-year payback periods, which is not ideal. So when you look at an individual aspect, it doesn't make sense. If you look at it as a building whole and the combinations you have, you might see a different outcome or perspective on that. And that's what this is really driving towards more than anything else. And then the last strategy is basically a energy recovery system, either doing it or not doing it. Obviously, the energy recovery system would be an added cost, but because this is in the Midwest, recapturing some of that expelled heat to heat up any recirculating air coming into the building will help be much more efficient because it is easier to move heat rather than generate heat. It's more efficient that way. That's why heat pumps are fairly popular right now because heat pumps do exactly that. They just move heat. Okay, so now that we kind of went through the difference of strategies, let's see if your mind have changed here. And here we're giving you a little bit more information here. We added energy savings range. You can see here some of these additional items are giving you negative costs. This is dependent upon the combinations. So once again, the strategies or the combos of strategies are still identical. So the previous selection everyone kind of chose was D, daylighting controls and HVAC demand controls. Let's see if, given the information we provided, if that has changed. So given the information we talked about, has your decision changed? Okay, so it looks like the group is seeing maybe envelope and daylighting controls as a much more efficient strategy, compost strategies instead. Okay, let's go through the results of what the group has selected. So everyone kind of selected A. Tina, what was the combination for A? It was,
The envelope upgrade and the daylighting controls.
okay, so that would be the dispersed massing, envelope upgrade, daylighting controls. HVAC was the base, no demand controls for the HVAC, and no heat recovery. Okay, let's see where we are with this here. Okay, so here are the results of what the group today selected. Here we have, you can see here, we're going to have an annual energy savings of $35,000 a year with an EUI of 60. Not bad. And oh, where's my mouse? There we go. Keep losing my mouse. Give me a second. All right. Okay. So let's go further with this energy analysis trends here and look at the overall results. So I didn't explain the chart in the beginning, but basically with the combinations of strategies we have, we figured there are 32 essentially combinations available with the 6 strategies we have. Okay, so we rank them by annual energy savings and basically percentages. So right now, that means we would have as high as a 40% reduction off of the base compared to the energy bills, and we can have as much as 65,000 annual energy savings. That's not bad. So in the range of possibility, there is 32 combinations available. And we'll go through some of these combinations and where they kind of lie here. So with the dispersed form combinations of the building massing, you can see here it's kind of peppered throughout. It has some high savings groups, but it depends on the combinations of whether or not you're going to have it with an ERV, the energy recovery system, and also looks like maybe mechanical as well. So it's a big factor, but you know, it depends on those combinations that you use, but you can see how it's kind of peppered throughout the combinations. The ground source HVAC combination is somewhere in the middle, and you would think because this would be the best system for this particular climate type that you would have maybe higher, and that outlier that is, get my laser pointer here, right here is probably in combinations with that energy recovery system here. So it's kind of dependent upon the combination that you're using with the, whether or not you're using it with the ERV and the additional controls there. And when we look at demand controls, once again, that is peppered throughout. So, you know, it's not a big driver in energy savings. It's going to be dependent upon the combinations, again, of the type of envelope, whether or not you're using an energy recovery system. That will be the biggest saver. And then when we look at the energy recovery combinations, it is in the top 9 of the board in rankings of energy savings. So just adding in an energy cost savings with the incremental cost of it can really help drive some of the additional energy savings, annual energy savings costs that you will see normally in a building. And then the envelope upgrade combinations, you can see here, it is a little bit more expensive, but it's also dependent upon the combinations of the mechanical equipment and whether or not you're using it with an energy recovery system, how much some of that driver would be of energy savings. And then your daylighting control, once again, not a huge driver compared to some of the other combinations that you will see here. So it's easy to fit anywhere within those combinations of designs that you're going to do. We usually call these the low-hanging fruits at the end of the day. Look for your big drivers first, and then pick your low-hanging fruits where you can, because as we may mention before, the costs for some of these are fairly inexpensive. And more importantly, and I think this is where the modeling exercises really play a big part, is understanding that here we have all the low cost combinations. And you can actually get some highly efficient energy savings without breaking the bank. You can see here, we have, even though with the ERV, the energy recovery system, depending upon the combinations you use, you can actually get some fairly high energy cost savings, close to 58,000 a year. Okay. With that, I would like to kind of pause if there's any additional questions that kind of came through. Okay. Moving along then. All right. So as we may mention, the optimal time to try to do energy modeling is always schematics or early design development to help determine what the simple and cost-effective systems would normally be. Of course, it's going to be, you're trying to predict how the building is going to use, and it's always important to actually also measure and verify how it's being used. We use the example of EUIs a lot like miles per gallon. Well, much like miles per gallon, is just dependent upon how a person drives or uses the building.
Hey, Ton, one question before you go on. Does the energy recovery savings model include the cost associated with installation of the system?
Yes, that is what the incremental cost would be of the energy recovery system. So when we said it was, let's say, $2 symbols, I think is what we said it would be. That is what we estimated the additional cost to the budget would be, or the incremental cost to the budget.
Thank you.
Okay. So what ended up getting built? Out of all the combinations, actually the funny thing is, the first decision that the group kind of decided upon was actually what the design team actually ended up going with. They went with the two most low-hanging fruits. A lot of factors played into this, but that's what they decided to go with instead. The reason why they probably didn't go with the energy recovery was because of maintenance. The school district was not too familiar with the system, so they didn't want to include that, and weren't sure if it would be worth their while to include it, and unsure how they would maintain it. So that's why they went with that. They still went with the dispersed form. They wanted the natural daylighting as much as possible, right? Because schools always like a lot of natural daylight. It helps with learning. So we understand where that aspect was, right? If we were to go off of strictly numbers, essentially, or values of modeling exercises, essentially we would always end up having a building design looking a lot like, well, I like to use the example of a Yeti cooler with a couple punch openings. That's exactly what, if we went strictly by the performance of an energy model. We know these decisions, we want to have that balance between basically the art of the building and basically the science of the building. And so we want to marry that up, and energy modeling kind of helps marry that up for you. And so you're somewhere in between.
Ton, in the chat, there's a question about, did they decide due to the code requirements?
The energy recovery, or what code requirements?
I'm assuming it's the energy recovery. Let me see if Jason will
Yeah,
clarify.
the project was based in Iowa. And so Iowa does not have an energy recovery requirements. And Iowa is based off of ASHRAE 90.1 2010.
Okay,
So
yeah,
there's no
this is actually base building code requirements.
yeah, base building code requirements didn't have an energy recovery requirement. So most of these strategies were really off of base code. And so the only thing that they went above and beyond base code was essentially the demand controls and the daylight controls, essentially.
Great, thank you.
Okay. So with the selection that the school district actually selected, you can see here, they had an EOI of 61.4, and they would have an energy savings of $33,000 a year. What is also interesting is actually, as they were going through the project, they actually midway through decided against the VAV system and decided to actually install the geothermal instead. Took a little bit of timing, but they managed to find additional spending. It did exceed their budget a little bit, but they were okay with it mainly because they saw the value in the energy savings. It moved them up instead of $33,000 a year. I think it bumped them up by another 10,000, so they were about $43,000 a year. And then in discussions or the group asking about the cost payback, or basically annual operational costs, they saw that with the additional $10,000 a year, their payback period for the additional cost of the ground source heat pump would be paid back a little bit faster than they anticipated. So that kind of helped them out in factoring in those decisions. And more importantly, when we looked at basically how the building operated or functioned afterwards, here in the green is what the actual energy usage was. And here in the blue is what was modeled. You can see here the trends are fairly identical to each other, but there's a bit of an outlier. Obviously, you're going to always have a little bit of a margin of error, right? Of difference between what is predicted and what is being used. But usually you're not going to have this big of a gap. Obviously, with all predictions, it's always based on, a lot of assumptions and averages. So you're always going to have a little bit of a margin of a difference there. But the reason why you can see here there was such a huge difference in the summer months was because what was unanticipated was the community really liked having a fresh new school building, that they ended up using it more than what they anticipated. So that's why there was a higher energy usage during the summer months. So that was unanticipated. The additional item that actually caused a little bit of that discrepancy is also a school teacher for one of their daylight controls in the rooms complained about it. And instead of basically trying to fix the problem, they just essentially turned off the daylighting controls. So essentially, any energy savings was null and void as a result. Once when they determined that was the case and recalibrated the controls, it was actually functioning as what was going to be predicted. So it was something to be understandable, but just because you have a difference of that, you shouldn't be too concerned. It's always worth diving into and understanding a little bit further of what some of those, why those changes or differences could occur. Once again, going back to, maybe the hours of use change, the function of the space changed. Maybe all of a sudden you had a higher plug load. This happens a lot with, core and shell buildings or multi-use buildings where all of a sudden a retail tenant takes up the additional space and then has the higher load capacity. Or even for hospitals, where also a use change for a hospital or clinic, and that space asset area changed. And that may cause a difference in the higher load usage. More importantly, also making sure the equipment is functioning properly, right? I think that is an easy fixable item, where if the equipment malfunctions, it's fairly easy to just go back, confirm if everything's working as properly, and fixing the problem at the end of the day. So with that, here are some key takeaways when we talk about evaluating a project's energy potential. With every project, every project is a little bit different. It's important to establish what those energy goals are early in design, especially when you're trying to utilize a model data to support your design decisions. Partnering with your electric providers will help you take advantage of some of those energy consulting services. And more importantly, remembering that people run buildings differently than is expected, and it's okay. Understanding what some of those differences are would be helpful as well. So once again, going back to that, much like the miles per gallon of your car, you can, your car may say 30 miles per gallon, but depending upon how an individual drives, that may actually be a little bit different than most. And we always like to end our presentations with a quote. This is from Donald Watson. If you're not familiar with him, he is a fellow AIA. What's interesting is he is actually the principal for the Earthrise design, was actually one of the few architects that was part of President Carter's task force that was put together for what is now known as the AIA Energy Committee. And his quote of saying, "Energy is a design topic, not a technology topic." So we should be incorporating energy design efficiencies within our design as we're going along here. As I made mention before, we really want to try to marry what is art and science together as much as possible. So that concludes our presentation. Here's our contact. We do have QR codes, so if you want to put your phone up with your camera and kind of copy that camera phone, you could actually download our VR card to your phone.